Hello, good evening, everyone. Can you hear me?
Yes.
Oh, great. So I think we are now at 8 p.m. So maybe we can kick our session. Okay, that's great. So just for the information, today's session will be recorded. Let me share my screen. Yeah. So welcome everyone to our machine learning paper reading club. And yeah, so this event is hosted by Women in AI. So across all the different Asia Pacific chapters. So to start off, right, let me introduce about what is Women in AI. So it's a non-profit organization, and we have founded in 2016, and we have altogether 8,000 members across 140 countries, including Australia, Taiwan, Singapore, Myanmar, and of course, we are expanding more to the other countries as well. Our main goal is to create an environment for women to own the stage and to give them the safe environment to present their ideas in the AI industry. So if you would like to like get the notification about all the updated event, you can become a member, and then you can even like become a volunteer or part of our Women AI. You can register in the link given below. Yeah. So back to like about our machine learning paper reading club. So this is the series that we have been hosting across the multiple weeks. And now we are at the middle, week 5. So let me give you like the recap of what we have done so far in the previous week. So we have kickstarted our event with the introduction and keynote, followed by the zero-shot learning through cross-modal transfer in week 2. After that, in the week 3, we have an introduction to the ROC analysis. And last week, we have a very interesting topic around adversarial AI class distance hardening technique. So for today, right, we are at the week 5, and for today's topic will be on the learning from imbalanced data. This is very interesting topic and very important topic whenever it comes to like building the model, like because in the real world we have like faced with a lot of imbalanced data, and this is one of the important steps that we have to be familiar with. So for today's sessions, right, our the speaker will be Thu Ya, and he's a developer advocate from Google Cloud. At Google, Thu Ya helps to make learning, developing, deploying, and scaling application on Google Cloud a delightful experience for everyone. Thu Ya loves to give back to the society. When he's not working or he's not coding, right, he actively organize hackathon or any of the like coding related events. Also conduct workshop, share his knowledge, and mentor the young generation of developers. He's such a great guy, and we are really lucky to have him as our speaker for today. So without further ado, let me invite Tura to like discuss about learning from the imbalanced data. And if you have any questions like throughout the session, feel free to type in the chat or like raise your hand, and then we will help you to answer any of your question. So the floor is yours, Tura.
Thank you. So let me share my screen. Okay. Thank you so much for being here today. So what we're going to go through is called learning from imbalanced data. Has anyone read this paper from start to the end already? Maybe you can say yes or no in the chat. Just want to see how many people had read the paper so that I can decide whether to explain in depth or you just go through from the overview. Has anyone read it? No. Okay. It has 22 pages, so I don't think we have time to go through all 22. But partially, I will just try to explain based on what I understand from reading this. Okay, so let's take like 1 minute to read the abstract together, right? Let's read it just the abstract. Don't have to go through everything yet. Just abstract, and then we can discuss on what we think this paper is about. So when you read a research paper, the first things that you should read is abstract, because abstract concludes of everything, the findings, the method that they're going to use, the outcomes of it, and then whether there is something that you are interested to read. Because there are 22 pages, and if we go through from introductions first, we will realize that we don't really want to read this paper maybe after 10 pages. Right? You already wasted the period from reading, page 1 all the way to page 10. So we should do by just reading the abstract, and we will quickly do that, like maybe 1 minute to just read, so everyone understand what this paper was about. Okay, I hope everyone has done reading the abstract. Anyone want to share what will be the 3 things that they will discuss in this paper? You can type it out from the chat, or you can voice it out by unmuting yourself. Or maybe just give one, like what are they discussing about in this paper? Okay, there's no volunteer today. Okay, so let's see. Yeah, oh, there's someone. How to gain insight from imbalanced data set. Yes. So machine learning at current stage work very, very closely with data, because we are trying to learn. Yes, okay, there are a few distribution, screw, yes, and the represented data, screw data, way to analyze them. Yeah, so current state of machine learning, we are using a lot of, we are depending a lot on data that we have, right? So there are other method of doing AI and some other things, but the machine learning specifically uses data from the past, and we are try to predict the futures, or try to cluster it, or try to differentiate it using the existing data set, right? And because there's more and more complexity involved in the networking system, there's a large scale data set system, there are internet, right? You guys upload to Facebook, TikTok, Instagram. There's a lot of surveillance system nowadays, and everything all come together. And sometimes when you collect the data can be very skewed. By skewed means most of the events, like the general events. Oh, okay, let's give it an example, right? So let's say you travel from point A to point B, right? Most of the time you can travel without falling down, right? So let's say you have a security camera in a place that is monitoring you traveling from point A to point B and recording it every day, right? So every day you travel from point A to point B, then what are the chances of you falling down? Is very, very slim, right? So if I'm going to use the recorded data of you traveling from point A to point B and try to predict when you're going to fall down, it's going to be very, very difficult, because the data set that we collected from that surveillance camera won't have enough data of you falling down, right? So you might not fall down totally. You might fall down once in like 3 months, right? So there's like 1 to 100 kind of ratio of data, right? So if you're trying to classify or predict whether you will fall down, it's going to be very difficult, right? Because you don't have enough negative sample, right? So the model won't be able to learn it perfectly in that manner, right? Because your data is not balanced. So that's why the importance of having this imbalanced data and the ways to train those data using the imbalanced data set is important. And in this paper, they also discuss things like not just taking care of the data set imbalance, but also measuring the accuracy of the model, right? So usually we measure things like F1 score, right? The R squared score, RMSE, and all these other matrices like accuracy, F1 score, like ROC curve, right? And they only cater for slightly balanced data. And even though the data are like not balanced, it might be giving you very good number on paper, right? But it might perform really badly in real life. So yeah, thanks so much for the input, right? Like distribution is skewed, that's correct. And like, how do we evaluate the imbalanced data set in this? So they're going to give you like the scenarios, and also how do we work with the data? How do we work with the model? And how do we work with the measurement, right? So these are the 3 things it's going to cover, right? Let me see whether I can highlight it. Right. So the introduction, you can just read it later on. So it just explain whatever things that I was just talking about. Sometimes there's a imbalanced learning problem occur, and then due to the ability to not being able to collect some of the small or skewed data, then we have to figure out ways to make sure that our model works with those imbalanced data, right? So coming to page 1, the nature of the problems, right? And even if your data set, let's say you have 2 classes to train the model, right? Let's say sentiment analysis, then you have a positive and a negative sentiment from a text data. And what it tried to address here is not so much of just 10 sample difference or 20 sample difference, right? It's trying to target to the imbalanced order of 100 to 1 ratio, 1,000 to 1 ratio, or 10,000 to 1 ratio. Right? So it's not going to be like, even though there's imbalanced data means almost every data that has not the same number of the data, but for the problem that they're going to target is just to the 100 to 10 at least, right? And the data set that they are going to use is a mammogram data set. And of course, there's like multi-class data which imbalance across multiple classes. So multiple classes means like various scenario, right? So going back to the example that I gave just now, you may be falling down, right? One of the day it might rain, one of the day it might be very sunny, one of the way you're walking with your friend, right? So those are different classes that doesn't really often occur often, but you still want to do prediction for those events, then it will be imbalanced data across multiple classes, right? Because maybe you only have one data of you falling down out of 100 recording. You only have one recording of you falling down, one record of you walking with your friends, and one walking with you when there's rain, right? So then you have like 4 classes, and you're trying to determine, you're trying to segregate or classify among those, and you have like one large cluster of where everything is fine. There's like 96 of them, and you have like one example of each various category. So to sort of save space, I think they already save some space by writing this paper, and they are trying to only target 2 class imbalance problem for this paper, and it took them 22 pages to show everything. So imagine if you're gonna do this for like a multi-class data, it's gonna be 100 pages, I think. So so let's go through this, and what they are trying to show you in example for this is using the mammogram data set, right? And the classes label are positive and negative, and also the image representing of, so positive means the mammogram is cancerous, and negative mean is not cancerous. Also there's some tumor or something like that. And there are 10,900 plus negative sample, right? Which is like majority of the people who doesn't have cancer. And the other is 260 positive, right? So this is like real life scenario, right? You don't really see a lot of people with cancers. And most of the mammogram are taken, and you have like false positive and things like that to taking care of, right? So majority of the population will have a negative, mammogram sample, and only a few who are unlucky will get the positive sample. So in this case, right, even though the data are not balanced, right, you try to train a model based on the input that they have. What's going to happen is, even if you get 100% accuracy on this, and you sort of like have 10% inaccuracy for positivity, right? That means you're going to have like 200 plus patient diagnosed as non-cancer when they are supposed to be cancerous or something like that. So it also works for the other way around. So if your model is like, even if 100% accurate, right, because the minority class only having like 10%, because it's 100 to about 100 to 10,000 to like 200 ratio, right? So it's like 5,000 to 100 ratio. If you get 100% accurate for negative and only like 10% for the positive, right, you still get quite a few number of people misclassified, right? And it is not right or a good thing, because misclassifying cancer have a lot of implication, right? So it can be costly, right? It can be it can create panic, social disorder, and you can get mistreated with the cancer treatment, and then you can cause some other health implication, right? So in this kind of situation is very, very important to taking care of those imbalanced data set before going through, just create a model, then classify something, even though the accuracy is good, right? And one thing to note here is the overall accuracy, right? It does not provide the adequate information, right? So let's say you train a model using this data set, right? With a 10,000 negative sample and 260 positive sample, you get like 90% accuracy, but doesn't necessarily mean that it's a good model, because you can just return negative, and that is simply cover 100, the accuracy cover just the negative, and even though you don't consider 260 as positive, the model will actually give you a very good accuracy, right? So if your model just return negative, because of the data is majority negative, your accuracy is very good, right? Because this is so small compared to the overall data set. So we cannot just based on those metrics that we work for normal kind of balanced data. So we have to come up with something. So they are saying that, curve, precision recall, cost curve, and everything that is supposed to be the conclusive evaluation performance of all the model and things like that, it doesn't work well for the imbalanced data, right? Even though your accuracy might be very good, but because of the classes in the minority, right, which is very small, and you probably couldn't get in real life, it won't perform well, even though you can get a good accuracy, right? So by working on these kind of problems, right, it could also improve, right, or yield a similar consequences in other domain, right? So now is a mammogram, which is a healthcare domain, but you could apply this to other domains like fraud detection or network intrusion, oil spill detection, right? Like I said before, sometimes let's say fraud detection, there might be only a few fraud happens over a very long period, right? Maybe in one whole week, you only have like 2 to 3 out of 1 million transaction, right? So in this case, it's very, very skewed towards the negative sample, and we have to figure out a way to fix this kind of thing. Same thing for network intrusion, right? Not every day someone will try to intrude your network, and you probably, sometimes you're new, right? There's no one intrude to your network before, so you don't even have that negative sample to begin with, right? Same thing for oil spill. So oil spill is like, it's not a good thing, so people don't really, focus on getting the negative sample, if I may say so. They try to prevent it with a lot of preventive measure so that there's not a lot of negative sample going on. Right. So from here, right, it's not just stick to the things that can happen, right? It can be because the collection process itself, you cannot collect more than what you can get. So for example, the mammogram, even though you can get for more people to like scan for mammogram, right? Because the chance of people getting cancer is small, right? You don't get a lot of negative sample, right? Generally speaking, the more people you invite to scan mammogram, not the chance of getting negative sample doesn't really increase, right? And the other one is when you collect the data, right, and you're collecting it wrongly, or you're collecting it with a bias, or you are unable to collect some of the data, right? So, for example, you are sending out a feedback form to customer and ask them about how good the feedback is or how good the product is, right? Majority of the people won't respond, right? And you cannot take those response out just because they don't respond you anything, right? You cannot just take the response that respond back to you and determine whether people are thinking about, positively or negatively about your product. Right? So you have to consider holistically from overall point of view, and this is something that they try to explain over here, the intrinsic and extrinsic balance, right? So it's like it's either relative to the imbalance in the data set, or it's imbalance due to the rare instances, right? The falling down, raining and things like that. So yep. So this mammogram data set is about 100 to 1, and they are expecting to have 1,000 minority class, right? So they are explaining here if you double the sample space, right? Even though you double the sample space, the distribution does not change, right? You get more people to sign up for this scanning, but even though you get more people, right, the negative sample distribution does not change. And the relative imbalance arise frequently for the real world application, because if you are focusing more on the knowledge discovery and data engineering research, right, there are a lot of things that we don't know yet, right? Like a lot of things that we don't know how to collect data. We don't know whether that even exists in real world. So often we are trying to focus on the research effort, and then things that we do might not be perfect to collect balanced data all the time. Right. So far we have discussed quite a few. Anyone has any thought to share? you can feel free to write it down in the chat, and then we can discuss, or you can unmute it and say, hey, I think you missed out this point that I really think is a good to share, right? Feel free to share, write it down, or unmute yourself and talk about it. I will give like 1 minute to write down some things or talk about some things, or maybe something that you're not clear about, right? Like, can we discuss a little bit more on this topic that we just go through, right? So we just went through extrinsic imbalance, extrinsic imbalance, and then having more people come to take the mammograms and things like that. Even though we have more people coming in, it doesn't really change the distribution of the data set and things like that. So if so far okay, maybe you can say, yeah, okay, let's go ahead, kind of thing, so that we keep this session interactive, right? Not just I speak and then. So Jason, you work with an imbalanced data set called Sabatel. Do you want to share more about your experiences with other scholars here? Maybe like 1 to 2 sentences, just explain what this data set is about, and how do you solve that multi-class classification using imbalanced data set. Okay, so the class 3 defects, it means, what does class 3 defects means? Okay, so it is more like you have a bunch of cracks on the surface and things like that, right? So Jason was saying in the chat, so he worked with the imbalanced data set before, and 2 out of 3 are just defects in the surface and wall and things like that, because you don't always see a lot of cracks in the HD, like the buildings and flat and things like that, right? Usually people will fix it before you even get a chance to get a sample, right? So it's very rare that you will see that kind of sample data. Yeah, thanks for sharing it, Jason. So yeah, we will just carry on, right? And in some classes, right, there's something like overlapping. So you are sort of like collecting data that overlap from one another. It may be you are asking the same person twice, right? It may be you are asking like cousins who has a very similar experience from one another, kind of thing. So even though you have a lot of data, right, some might be overlapping, and some might not be able to represent the data, and also some might be very, very small, right? Small data set which doesn't give you a lot of information to represent one class, right? And like they are trying to explain in the sense of you have a data space, and then you are trying to get a sample. Sometimes the cluster dominate the others. Sometimes some example outnumber the others, right? And sometimes you have a subclass from like let's say you have one big circle, and the circle is split into 2 clusters, right? And 2 clusters in the middle, you have more subcluster, right? You can take a look at this example, right? So the image A, you only have 2 classes, right? Like one star and like one circle, right? Star are in the center, and the circles are always like surrounding, and you also have noisy sample, which is just out of reach or out of cluster from the star, right? So if we want to sort of learn from this, we will try to build some model that just select the star from the middle. But if sometimes, right, even if you go down deeper, then you will start to see that the majority of class, right, and it can further split down into 2, right? So the general majority class and then majority class set concept, right? So even though they are all circle, and some of the circles are actually fade out with something. So it is like circle, but bigger maybe circle that has more attribute to it. And same goes for the minority class, right? So when you go deeper, you have the general minority concept, and then you have the minority class set concept, which is a very niche, kind of unique kind of situation from both classes that arise, right? And if you are going to build some cluster or some classifier, which means model, it will try to, if you are building this kind of, if you are building model using this kind of data, it will try to build by creating a multiple disjoint root, and then that try to learn the main concept, right? Homogeneous in this case, it means that it try to split, right? So the model try to draw lines for each of the classes, and the more cluster you have, the more disjoint you have to make from a model, and then so that you can combine all these things together. So if you're familiar with things like one versus all kind of approach, and you have to create multiple models just to be able to split from multiple classes. So you have, let's say you have 4 classes, right? You build one model that determine one class versus the other classes, and same goes for the other. So you have to create 4 models just to split the 4 classes together, right? And they further on to discuss about the imbalanced data with a small sample size problem. So having imbalanced data itself, right, is already a problem. Then now they try to merge that together with a small sample size problem, right? So in machine learning, you have to have enough sample size that is representative of the data for machine learning to learn, right? So having small sample size is also a problem for machine learning, right? So if you have small sample size, you can't learn enough so that the models doesn't do well, right? And now we are combining that small sample data size with the imbalanced data, right? So this is like problem over problem, and it's often unavoidable because there's not much data have to begin with, right? So they say high dimension and small sample size. There's high dimension means you have a lot of columns, right? So in your data set, you have a lot of columns or features, but you only have a few rows, right? So your model have to be, let's say you're creating a machine learning or deep learning model, right? Your model is very, very wide, right? But there's not much sample to train those weights, right? So, and they're trying to say that something like face recognitions or expression analytics or things like that, right? They often have this kind of data where there's a lot of high dimension. High dimension means the image have like 3 layer of metrics and things like that, but you don't really have a lot of sample size to go through, right? You don't get to take a photo of a person, let's say 10,000 times, right? It's very unlikely that you don't have that kind of data set. And well, what they are trying to do, what they're trying to point out here is that the small sample size problem is, been studying for longest time in the pattern recognition community, because you don't get to take pictures of a person multiple times. And for the high dimension data set, they will try to use things like principal component analysis to dense it down, right? Try to reduce the dimension of the data so that your data is not very wide, right? So we were doing, let's say if you're familiar with CNN, things like the map reduce or the map pooling and all these things are trying to condense the information into smaller, the features, so that our final descriptor has better time understanding what model, what is particular image represent. So yeah, so having those imbalanced data set and a small sample size, right, is present a new challenge altogether, right? So they were explaining first, there's a sample size is small, so all the issues that are related to the rarity within class imbalance are applicable. Then second, the learning algorithm failed to generalize because some of the samples are imbalanced. So imbalanced, small data, right? Right. So, and it tried to highlight things like, okay, this is a new research topic, is require much attention, right? So they will only touch on this later again. So they don't really want to talk about it right now. They will just talk about it in a later time. So now here, so everything here that we just read is to describe all the things that went wrong with having imbalanced data, right? Extrinsic, intrinsic, within class, imbalance, different subclasses of imbalance, and how imbalance can cause problems, right? How imbalance plus having a small sample of data set is a problem for the research community, and we need to have a good way to sort of solve these kind of problems, because like they gave an example about mammogram, right? Being able to identify cancer patient would be a very particular thing to do. If we sort of detect it wrongly and didn't detect some of the cancer patient, is going to have implication. Even if we detect it correctly, right, or we detect the one that not cancerous as cancerous, is going to cost them money and have implications. So we have to really focus on solving these kind of problems as a research person, right? This is what they are trying to say, right? Yeah. So someone has a question, you can type it here and we can discuss, right? Or so far, anyone has any thoughts, want to discuss, or want to talk about it, or want to share something? You hold a different view. You think I missed out something, you want to highlight? Just go ahead. Feel free to do that, right? There's no judgment here. Yeah. Go ahead, Miu Minko.
Hi, can you hear me?
Yeah, we can hear you, Mimiko.
Okay, I just want to ask you something like, I have a little bit confusion about within class imbalance and between class imbalance. So I don't know like how to differentiate between these two terms. So can you explain me a little bit?
Sorry, I think my headphone wasn't working. Can you repeat the question again?
Okay, so can you hear me right now?
Yeah, I can hear you now.
Okay, like I have a little bit confusion between the term, like within class imbalance and between class imbalance. So can you explain me a little bit more about on it?
Okay, that's fine. Within class. Okay. Within class imbalance. And sorry, what's the other one? Within class
and between class imbalance.
Okay, so within class means, so let's take a look at this diagram. Let me just zoom in. So between class is the picture A, where you have imbalance between two classes, right? So one class is smaller, so much smaller compared to the other classes, which is really big, right? So in the feature A, or in the figure A, the stars are the small, the minority, and the circles are the big one. So imbalance between this class is called between class imbalance. So far, so good?
Yeah.
Yeah. So, okay. So let's take just the circle, for example, right? So we ignore the stars. We have a circle now. And within the circle, they have a differentiation. Like even though they are all circle, some circles are different. Like which is the bottom one. They are circle, but maybe a little bit bigger, right? But they are still a minority. So out of, let's say, 100% of this circle, right, 20% of them are different, even though they belong to the same class.
Yeah.
Yeah. So that's something like within class imbalance, right? So maybe the example would be, let's say you have 1,000 records, right? Maybe only 200 of them are discrete enough to to learn the data representation of that data that you have. So out of 1,000, only 200 of them are good. Just an example, and you can sort of see there's a imbalance within class, right? So how do I say? Let's say you have you are doing a sentiment analysis and try to determine positive and negative, right? And within the positive, you have very positive and positive. Within the negative, you have very negative and negative, right? So very positive and the imbalance between very positive and positive is within class imbalance, and imbalance between negative and positive is balanced class imbalance, between class imbalance. Does it make sense?
Yeah, I got it. I think I got it. So
Yeah.
like, okay, can I tell you something that I got it?
Yeah, sure, go for it.
Yeah, so like by explaining to me like that, so I understand. So between class imbalance, it's a kind of between two classes. So it's a between class imbalance.
Yep.
And then within class imbalance, it's just like nesting. So it's just like so imbalance like that is nested in one classes. For example, like if you have a one classes and you have a subclasses.
Yep.
Inside it. Okay, this is a within class imbalance. So,
yes, that's right. So yeah, it's like very positive and positive is within class, right? They are all positive as a bigger family, right? So the problem with it is if you are just determining positive versus negative, right? You only have to concern about between class imbalance. But if you are further breaking down into 4 classes of very positive, positive, very negative, and negative, you have to also start to consider that within class imbalance.
yeah, I got it. Thank you so much.
Yeah, no problem. Anyone had any more questions? We still have 20 more minutes to go. So, and there's a lot of people. We only have like 3 pages, and it's a 22-page long paper. So we can go ahead, right? So we are actually here. So right, so this is like the problem with having all the data imbalance, right? Cannot collect the negative sample enough. Is not because you cannot. So one is you cannot collect, right? There's nothing that you can do because it's based on the distribution, right? Let's say getting more people to take the mammogram test doesn't solve our problem. And the other is you are collecting from a biased data space. So you are trying to collect it, but you are not being able to collect it in a balanced manner, right? Even so, that kind of thing, you can sort of solve it by changing it. So you try to collect in a correct way, but we are still trying to do research and try to find a better way to collect data and clean the data and all this. So those are underway, but there's another way that we can also solve this thing. So now what they are trying to do is to propose the state-of-the-art solution by how do we then solve this imbalance learning, right? So they are going to propose quite a few things, right? So they say here that standard learning algorithms focus more on the existing solution, right? And when standard solutions are applied to the imbalanced data, the induction rule describes the minority concept, often fewer, right? So let's say I'm going to train my model using 100 records, right? 90% of them are positive and only 10% of them are negative, right? And if I train my model using that data set, and if I want to infer my model, right, or use my model in real life, my model will tend to use or tend to give out positive label as a result because I train more on the positive label than a negative label, right? Let's take a step back and think of an example, right? Let's say you go to a gym and you train both of your arms, right, by carrying dumbbell or carrying weights, right? And you train your right hand 100 times, right? But you only train your left hands 10 times, okay? And you do this for maybe like 1 month, and one day I ask you to carry very heavy weight from your right arms, you might be able to carry it, right? But your left arm might not be strong enough to carry because you didn't train enough. So whenever I pass you things, you will tend to use your right arm because your right arms can carry a lot of heavy things, right? Because you train on it, right? So model will be tend to bias towards the one that have trained on more frequently, right? And also they talk about partitioning the data space, right? And when you try to partition the data space that you collect data, right, the more you partition it, right, the fewer observation. And it's like you collect 1,000 people, right, only 20% of them has something that you want, but you split it into 500, then only the more you partition, the fewer leave describing. So they are trying to use this they are trying to train some algorithm using the decision tree. So the decision tree, they use decision tree. Decision tree is something like, you split the data into condition. So let's say it has certain criteria: yes, no. If yes, go left. If right, if no, go right, kind of thing. So if you use decision tree in this kind of imbalanced data set, right, it's going to be partitioned in multiple way. And since you only have a very few negative sample or very few class, it's going to get split further, right? The more you go down into the tree, it's going to split further, and then fewer and fewer minority class sample, right? And if you keep doing that, it's going to have a weaker confidence estimate for those classes, right? And right then this is more like explaining why when you use decision tree model on the unbalanced data, some of the problems, right, is like relative or absolute balance, right, correlate with the best class imbalance and problem high dimensionality. So the more dimension you have, the more branches that you will have, and then the more branches that you have, you are going to further split down all the minority classes, and then it will have less and less data to learn from for the model, right? I might not be doing justice to all the equations here because it's very hard to explain equation online and when I'm not writing something, right? So I will just skip this part and try to go to this sampling method for imbalanced learning, right? So since our data is not balanced, right? What we can do is to modify the data set and try to make it balanced, right? So let's say I have 100 records, right? 70 of them are positive and 30 of them are negative, right? What I can do is I can try to find a sample from the 70, right? Take 30 out so that I have 30-30, right? So 30 negative, 30 positive, because I take a sample 30 from the 70. Then I train my model using that 60 data set instead of over 100, right? And because if you do that, sometimes the sampling method, the sample that you extract from those data set cannot describe the data set as a full, right? So of course you have 70 records for that particular class because you're only taking the 30 from that 70, right? The 30 may not be able to represent your data fully, right? It will sometimes, right, make it unable to learn correctly, right? So even though in that kind of situation, right, the paper says here that most of the imbalanced data set, sampling technique does help improve the accuracy, right? So instead of just training on 70-30, sampling 30 from the bigger set, make it into a 50-50 data set, is likely perform better compared to training everything overall, right? So now we move on to this thing called random oversampling. So random oversampling it means that you are oversample, right? So oversample means you are touching the minority class. You're trying to make minority class bigger. Undersampling means you are trying to make the majority class smaller. So oversampling, it means you try to, maybe you create a bootstrap data, right? So maybe you are trying to create multiple records or the multiple observation from the minority class. Maybe you copy multiple line, make it duplicate, right? Then change a little bit here and there to compensate your duplication, right? So by doing that, you are sort of balancing out the distribution of imbalanced data set, right? So it's very natural, right? You just add more sample from the minority to the minority. That the minority become bigger and is somehow balanced, right? So then oversampling so there are two methods, right? So oversampling appends data to the original data set, right? Because oversampling means put more data to the minority. Then random undersampling, it remove data from the original, right? So those sometimes doesn't give very, even though it sort of make it balance, it's not the best way, right? And if you really think about it, oversampling and undersampling seems like they are sort of doing the same thing, right? But they introduce different problems to the data set, right? So like I mentioned before, if you are doing a random undersampling, means you take sample of 30 from 70, and then you train it, right? The 30 sample that you took may not be able to describe everything about the data set. Then the same thing about the oversampling, because you are making duplicate from existing minority data set, right? You might be overfitting that minority because there are only a handful of minority example to learn from, right? Even though the sample number goes up and become equal, right? They introduce some other problem by itself. So it's trying to say here, so the removing the example from majority class is causes the classifier to miss important concept, right? So like I said, the 30 might not be able to represent the whole thing. And you can overfit if your oversampling occurs when the classifier produces multiple clauses to have a multiple copy of all the example, because you have a lot of duplicates in that minority data set, right? So it's trying to overfit to the minority. So even though your data set is balanced, your data set quality is not good, so your model cannot perform very well. So that's what it's trying to tell. And anyone want to discuss about this topic? Or anyone have any thoughts, any questions about random undersamplings and oversampling? So far, so good. Did I explain really good? I'm just smoking you guys. I haven't read this also. So I'm just reading it. And there's no, so Jason asked, to be safe, do we go down, do we do downsampling first? So downsampling is a safer way compared to upsampling, because, and it also depends on how much down you want to downsample, right? Like let's say I have 100 records and 10 records. I cannot downsample 100 down to 10. That is like very much further away from the original data set, right? And so if you are going to talk about, let's say 100 versus 70, okay, that makes sense to downsample, right? If you are talking about 100 to 10, then you have to do something else. And sometimes you can combine the two. You downsample to 50, then you upsample to 50. So they sort of match together. Yeah. And I mean, the way I'm saying is more like try and error approach. And in this paper, they sort of recommend using multiple things. So we can go through that, right? So since we don't know whether we should upsample or downsample, right? There is this thing called informed undersampling, right? So informed undersampling is there are two algorithms that do that. It's easy ensemble and balanced cascade, right? So you can take a look at what they do, right? So easy sampling is you develop an ensemble learning, right, independently on the several subset of the data. So if you are familiar with like cross validation, is somehow similar to this. What it does is it just split your data into multiple subset, right, and then try to develop multiple cluster, right, and then it will try to combine all these subset for the minority class, and then it's assemble back. Assemble means it may be just combine all the weights and get the average of the weights, or it may be combine and then get a majority voting kind of thing, right? And the balance cascade is more of like supervised, right? So you systematically select, right? So maybe your model is predicting, you have like 5 model that is predicting very well. Out of 5, there are 3 that are predicting very well for the minority class. You might just pick that 3, or maybe it's just 2, right? Instead of picking all 5, you just pick 2 to get an example, right? There are a few examples here, right? And what you can also do is you can create a sample using k-nearest classifier, right? The k-nearest classifier is something like this, right? You try to find the centroid of each cluster, and then you calculate the distance. Let's say this is like the centroid, right? You try to calculate the distance from the centroid to all the points. Right, so from all the points, you calculate, and then if they are within the distance, you take them as one class. If they are out of it, like for example, all this particular circle, they are not within the same class, right? So figure 1 is an example of k-nearest neighbor under the consideration of k equal to 6, right? So k equal to say 1, 2, 3, 4, 5, 6. So it will take 6 particular data point and then form a centroid. And then when you try to generate the data using k-nearest, it will just calculate using the distance. So maybe, this point, you can create one data set because it's still within the region, right? So the region itself is like this, right? I don't know whether I can draw. Can I draw? No. Okay, so it's like within the region, you can put some data in it, right? So it's like within the region, you put more data in, it sort of make you feel like there's more data to be collected, right? So that's what they were trying to do, right? This is there are 3 near miss method. So near miss 1, near miss 2, and near miss 3, right? So near miss 1 is one majority sample average distance to the 3 closest minority class, right? Then they will just put it 1. And for near miss 2, average distance to 3 furthest minority class. And near miss 3 is more of the closest majority example, each minority example to guarantee there's a minority example. So you have to like read it and then try to point it out on the maybe you need to read further on which, not sure whether this explained. It seems to me that what it's trying to say here is based on the distance between majority and minority classes, it is trying to calculate the near miss, the sample data. So this is trying to determine whether you should enter sample or not, right? So each particular data, so this is like majority, right? And how do I know which sample I should remove by enter sampling, right? You can use k-nearest to determine, okay, this is good enough, so I remove this, or this is following the near miss 1, near miss 2, or near miss 3, I removed it, right? So this is what it's trying to explain here, right? So near miss 1 is 3 majority example, every distance, and then try to remove it, something like that. So these are like a formula to remove for ender sampling. So far, so good. I will finish. I think I will try to finish the data generation one also. So I didn't explain very well for this near miss 1 and 2. Just take it as there are methods for you to calculate a value so that you can remove the ones for and the near miss 1, 2, or 3, right? So when we was undersampling, initially, we're just doing a random undersampling, right? So we don't want to do it randomly. We want to do it like more carefully, which means informed undersampling, and we calculate it using like k-means. For example, we have near miss 1, near miss 2, near miss 3. We can remove those near miss data set, right? The near miss in data from the row, right? So another way, so this is more of oversampling, right? So this is undersampling. Oversampling by doing data generation, right? So data generation method is, one of the method is called SMOT, synthetic minority oversampling technique, right? Is create artificial data based on the feature space similarity, right? So instead of just creating a duplicate of the data that you have for the minority class, it try to create something that is similar in feature space. So not just not the same, but it's similar, right? So it is also use k nearest neighbor to determine the Euclidean distance, right? I think this is what it's trying to do. Data created based on Euclidean distance, right? So like I explained just now, using the k nearest, you form a cluster, then whatever that is within the cluster, right, based on the distance, you generate it. So this only have 2, 4, 6, 7 data set, right? Then you calculate the distance, and then you put 1 here. So now you have 8, and you put 1 here. Now you have 9, right? So even though you are putting it all here, and each like in the middle of all the lines, they are still considered one cluster because they are within the same sort of like cluster, right? Initially, we were just duplicating whatever star we have, but now we are smarter. We try to put somewhere close to the stars, right? So it's like similar, but not the same. Right? This is the SMOT method that we use. Yeah, so SMOT method also have the drawbacks, right? Including the overgeneralization, because the cluster that we just defined, and maybe I just show here. So this is the cluster we define, right? But there's no telling the cluster has to be within this particular circle, right? It could be that the cluster go over the circle, right? Then since we are just considering whatever within, we might miss out whatever outside of the cluster. This is what I'm trying to say. So it will just overgeneralize, and then there's no variance, right? It just reinforces that cluster as a cluster. It doesn't introduce another stuff, right? So far, okay. Any questions about the adaptive sampling? And we are already at 9 o'clock, and let me just quickly finish it. Right, so this is adaptive synthetic sampling, right? So SMOT generate the same number of synthetic data for each original minority, right? So you are just considering that cluster and then generating new data inside the cluster, but it never consider how close each data is to the other data set, right? So you have like 5 data points, you just keep generating data, but never consider whether it's like how close are they together, right? Whether they are the same or not. It doesn't consider that. SMOT doesn't consider that. So they try to do some various adaptive method to sort of like rectify that kind of condition, right? So one of the one is called danger method. So danger method is, let's say you have this kind of condition where the majority class and minority class are very close to each other. And if you happen to generate 1 star on top of this circle, it's a danger kind of distance, right? So let's say they say for A, instance 2 and 4, which is like danger, I think this one. So because the star should only take stars, because you generate it, right? It sort of reinforce that clustering logic, and then you start to pull in all the others clusters also. Right, so there's danger, there's noise, and there is another one called safe. So we will want to only generate within the safe instance. So this is one way to calculate it, right? So we don't just want to populate data within the cluster. We only want to place the data within the cluster, but also has to be safe. Right, so this like more step to further sort of like clean the data that you put in, right? So one time we just randomly put anywhere. Also started with we duplicate the data. Then the other after a while we sort of figure out the problems. So we try to train KDRS neighbor, and then we only put within that cluster, right? And then now we are smarter. So we try to put within the cluster, but we consider the distance between each point. And now even we are considering, even though they may be within the distance, but it has to be safe. Right? So it's keep adding in additional condition when you generate new data, when you generate the data for minority class. Right? So this is what trying to do. And sometimes you can also do sampling using the data cleaning method. So when we try to under sample, right, we are just randomly dropping or picking some of the data set from the majority class. But after we generate all the data, we can also do data cleaning to remove or make it balanced again, right? So there's an image about this. So this is the image that try to use data cleaning to make it more normal or make it more balanced data. So this is like original data set. So this is the original data set. And then they are going to use the smoke algorithm to generate some data, right? Smoke only consider the distance between each point. So it doesn't consider whether they are safe or not, right? So as you can see, some of the stars are overlap, right? Some of the stars are everywhere. So it's only just consider the distance between each point. But this is not a very good data set because everyone is going everywhere, right? Like you don't really have a clear line on what to cluster. So C, they try to form that, sim link, like how different clusters, they are close together in a certain distance, and they will try to identify those two of those records, right? Two records very close to each other, and they are different label. So from here, stars and the circle, they are different label, but they are very close to each other, right? So it's the same for the rest of the incidents, right? Stars and circle, they are very close to each other. So instead of just using this, which is going to make the model confused because they have a very similar features, but the labels are totally different, right? So to be able to have a very descriptive data set, they just identify this using Tom links, and then they removed it. Right? So once they removed it, you have left with this kind of data set, which is very descriptive of the space, and also a lot more data than initially. Right? So initially they have 3 here, and they have 5 here. Right? Because of tumbling and generation, now we have 6 here and 3 here. And we also remove some of the majority class. So we also under sample at the same time. So we oversample the minority and under sample the majority. Right? So this is one way to do it. And yeah, so wow, this already 9:10. Okay, so there are some questions. So maybe I'll just answer some of the questions. Jason asks, do I have any best practices of dealing with imbalanced data? Best practices, it will be fairly depends on your data set, right? You can follow the same approach that we have, right? You can just simply undersample, a random undersample or oversample, and see whether that sort of enough to solve your problems. If not, right, you can do informed undersampling, right, and see whether that helps. If not, you can just keep on going, right? So not necessarily have to go all the way to the state of the art methods to do, because there might be a lot more computationally expensive to create stuff. And this is really good because every iteration or every new steps, right, they try to tell you, okay, this is what we do and this is the problem. So we try to counter that by having proposing this new method, right? So you can also follow these steps, right? Try random undersampling, try adaptive undersampling, and then you try to do oversampling, you try to do synthetic data generation, right? And you try to do smoke data generation. You try to create try to use data cleaning like tumbling to do this. Gangs is basically what they do. So gang is generated adversary networks. So gang is also, so the gangs in this context is I believe is more to generate a similar data set, which is clearly what we did. So we did this, right? Synthetic sampling using data generation. Right, so smoke probably one of the gangs, I think. We can try using gangs to generate. So I have seen some people use, so they learn the variance, like statistic of the data set that it exists, and then use gangs to create more data that follow the same distribution, right? So it has a same distribution of whatever you have, but the data are not the same. You can try that as well. Yeah. So Angeline asks, given the different method mentioned to have solved the class imbalance, is there an order of preference or which method is the most or less preferable? I think, like I answered just now, is fairly based on how complex your problem is and also how critical your problem is, right? Is if you're trying to do like healthcare system, and you should put more effort into making sure that your data are not biased, right? Your data are not imbalanced. But if you are going to do, let's say, just for learning, then the simple method should be able to work, right? So it will fairly depends on how much effort you want to make it work, and also how important particular thing is, right? If your task is very, very important, you better use the state of the art and then everything that you can to try to find the best possible method to enter and oversample. Right, I hope that sort of solve it. And this is only data side, right? So we have 3 side: collection side. This is more of like generating side, right? Trying to change the data distribution, everything. They also have another side where you try to change it from the model, right? So maybe let's say you have imbalanced data and you cannot do this kind of sampling. You cannot change the data in any way, right? And you are trying to tweak the model to learn more from the minority class, right? So if the label is minority class, you have a different side of multiplier to update the weight compared to the majority, right? So if your class are majority, you don't update so much, right? You don't influence the model updating so much. But if you are training on the minority sample, you amplify it, right? So your model sort of like balance in that manner, right? Even though you don't have a lot of sample, it's like your sample updates strongly to the model instead of they are all the same. So there's also other ways. So it's all the way down to like a few pages. So these are all data stuff, right? You try to do data cluster-based sampling, generate. This is where the learning come about. right? So they have like cost-sensitive method of learning, right? There's some other learning that is involved. You do cost-sensitive decision tree. So cost-sensitive in that manner, in this sense, means you're trying to put more multiplier to the minority classes, right? So your minority class, even though it has a very low count, the intensity to train is higher, something like that. Yeah, I hope that solved. Yes, okay, awesome. Anyone? I think we cannot go through the model part already because it's already 9 plus. Feel free to like read slowly and understand, right? So imbalanced class is to recap everything. So we went through from the abstract, right? Imbalanced class is a very serious problem. They gave example of head care, right? We have a mammogram data set which is imbalanced, and even though we get more people to come and do mammogram, we cannot get more negative sample because by distribution, not a lot of people get cancer, right? So then they are trying to find out what others imbalance there is, right? So sometimes is because of the distribution in nature, you cannot get more data. Sometimes is the way we are collecting data is imperfect, right? So we have to put in more effort into research and finding more methods to do data collection so that when you collect the data is balanced. If we cannot do both of that, right, then they come in and talk about different type of imbalance, right? The between class imbalance and within class imbalance. So it's like very positive, positive, negative, very negative kind of thing. Then after that, they talk about, okay, if we cannot collect more data, or if we cannot collect the balance data, how do we solve imbalance, right? So they introduce the oversampling from the minority class, then undersampling of the majority class. Then once this is done, is explained, you just randomly undersampling doesn't help because whatever you sample may not represent the data fully. So they introduce the smarter way to undersample it, right? The adaptive undersampling, informed undersampling, right? So informed undersampling. After that, you have oversampling. We generate data by just replicating the entry. So after replicating it, it start to see that there's a lot overfit, right? Because the data are the same. So they have to be smarter about how do we oversample stuff, right? Oversample stuff by using, let's say, k-means. So k-means come up with a cluster, right? We just put data within that cluster and we create more data. But that's also sometimes doesn't work because you might go and paste it on top of like the other class, right? So now we have to start thinking about where to put those new data set. So new data set has to be put only where there's a safe to put, right? So they try to calculate the distance between other class versus existing class, right? So let's say you want to put one data into that cluster, you got to calculate the distance of, okay, how close is this to the other class? Or how close is this to the same class, right? So there's like near miss 1, near miss 2, near miss 3. So you do all this. After that, they also find out that even though you do this, it's not enough, right? Because you might be putting in very close to one another and start making your model confused. And they try to do this thing called the data cleaning, right? T-link. Right? So try to delete whichever has same class, a different class, but they are very close to each other, deleted. Same different class, very close to each other, deleted. Right? So generate more data, same class, very close to each other, deleted. So the more they do this, the further away each classes are, and you have a distance, way to differentiate each classes, right? So you do undersampling and oversampling at the same time in this case. Right, so this is where we left off, right? And now is the cluster-based sampling method, right? So there's other things like smoke with other boosts or smoke boosts and all these other things. So have a take a look at it. Now it's already 9:20. We are 20 minutes overrun. If you have any questions, write it down. If not, we just call it a day.
Hey, yeah, thanks to for a very detailed explanation, and yeah, thanks the audience for like staying late. We believe that it's a very useful sessions for you guys. And let me share my screen. And then yeah, I just want to introduce you with our next event. Can you see my screen? Can you see my screen? Yeah. Okay. So yeah, I it's a very interactive sessions that we had, and then yeah, we see like people are like very interested in this topic. But like next week, right, we'll be having the same topic, but next week will be more from the point of like how we use it in the real life, and also there will be some hands on the notebook session. So do join us if you are interested. And yeah, and if you haven't connect with us, we are available on the social media like LinkedIn, Facebook, and then you can also email us if you have any questions about today topics, or if yeah, you want to like connect more with the speaker. And also the sessions recorded, so all the sessions can be reviewed later at our YouTube channel. And also, yeah, if you are interested to be part of the Women AI, or like you want to be contribute back to the society, right? We are looking for volunteers as well. So if you are like you are keen, feel free to drop email to us. And also, yeah, thank you for your session. And I would like to take a few minutes of your time to get the feedback so that like we can improve further for our subsequent sessions. Thank you so much. I will twist the link in the chat. Thanks for your time, everyone.